Thank you all for coming. I know you have a lot of things to do at the March meeting, and I really appreciate you being here. I want to talk today a little bit about Qolab and what of our kind of big commercial interests are. We are collaborating with Quantum Machines in terms of the control electronics part. We chose them because we think they're a really good partner in terms of making quality qubits, and we're working very well together, very closely together. I want to try to give you a take-home message, and the take-home message is for Qolab, it stands for quantum collaboration, and we really want to collaborate with you, our customers, to build better qubits. And we think you're a very big part of what we want to do, because when you test our qubits, you're going to be stress testing them in different ways, and we're going to learn from that, and because of that, we're going to make better qubits. So we really, appreciate that. Now, another way to say this is if the people out there want to build a quantum computer, please come talk to us. But there's lots of other companies out there that can build quantum as well and sell quantum computer chips. And this is great. We think it's a good ecosystem. All this is fine. However, if your goal is to build the quantum computer, the best quantum computer in the world, please come talk to us, because that's what we're really focusing on here. And for example, yesterday, that's why we're making these very high quality qubits in a special foundry. There's other things we're doing here. So that's our goal, and we want to make the qubits a lot better, because that's what we're going to have to do to build a useful quantum computer. Next slide, please. I showed this yesterday and talked about how the rate of growth is kind of slow. And I want to build a useful quantum computer before I die. So, okay, let's speed it up. I have to admit something here, is I really didn't quite tell you how I felt about this yesterday. And with this small group, I can talk about that. And I think the situation is even worse than what I was talking about yesterday. It's going to be harder. And things are hard at 10, 100, maybe 1,000 qubits, but it's not going to get easier to scale it up to 1,000,000 qubits, okay? So we really have our work cut out to do it, and that's what we're trying to do with both doing the fabrication, control electronics, everything. One of the things we're talking about right now is if you're out there trying to do research on qubits and this kind of research, to run these quantum computers, it takes, let's say, a graduate student or a researcher who's basically a race car driver. They really have to know what's going on. It's really, you have to, take the turns really carefully. We want to build quantum computers that are better in the hardware, better in the chips, better in the software and whatever. So it's least like driving my Toyota, that it just works. And eventually we want it to be like a self-driving car. Now it's not going to be fully self-driving, because we're physicists and you always want to contribute to it. I get it. But we want to make it much easier. And we really think by, for example, getting rid of the TLSs, we can make, which I talked about yesterday a little bit, we can really make these devices much easier to operate and much better and the like, and make the control easier. Okay, next slide. Okay, so the Qolab plan. We want to build very advanced qubits. We have these targets. And in fact, there are talks out there that the hero qubits are beginning to do that. We have designs for a fast 2-qubit gate that can be 35 nanoseconds long. And the intrinsic errors of that gate is in the 10⁻⁶ level. So it can be made really, really well, at least according to calculations. And then by operating that properly, and even in an array, we think we can get the intrinsic errors down below 10 to the minus 4, but in practical, because of T1 and whatever, it's going to be in the 10 to the minus 4-ish range. So people are beginning to do that. That's what we're pushing for. That's what we have designed for, and the light. And of course, in the end, we're trying to build it in a scalable way, 300 millimeter fab. Our thesis, and I'd be happy for people to show us wrong, this can be done with tunable qubits and couplers. You can build the architecture right. Second thing is we want to build very high quality infrastructure. So again, excellent control with quantum machines. And what we're doing with quantum machines is we're actually stress testing the machines to try to get to these low error rates. And we're working together very well to make sure everything is working properly. And this is it. We also need to build special equipment, talk about that, to make sure that the devices are working properly. And then of course, for all of this, we need DC flux control. And that adds a lot of complexity to it, and you just have to live with it. And if you talk to any microwave engineer, you never want to have like DC control. It just breaks the fundamental engineering. But you need to do that because that's how you're going to get super fast and super accurate gates. And to help do that, we have custom chip mounts. I'll talk about that. And we also have to make sure that the noise is low, and we're building testing infrastructure to do that. Next slide, please. Okay, so collaboration plan. Our basic plan here is that whatever we're doing in our lab to make the best qubits, we're going to share with our customers. This is both the devices, the qubits, our chip mounts, but probably more importantly, like the intellectual infrastructure. How do you set up your lab so that you have low noise, so that when you turn on the lights, you don't get switching power supply noise on your qubits, things like that. We're being very systematic, trying to understand that, working with quantum machines so that you can have state-of-the-art measurement capabilities. And I'm going to just say, we're pretty good at this, okay? So you get advice from some of the leaders in the field here. And again, I really like this model because when you go out and use our equipment, you're going to be stress testing it. You're going to be doing things that are a little bit different. And if it doesn't work out, and we're going to talk to you about it, we're going to learn more about how to do this. And it's going to boost up our reliability of making these very complicated machines. So that's a great advantage to us. So I would say it's a little bit unusual to be sharing this infrastructure, which companies typically want to keep secret because, it's hard to develop and that's their secret sauce. And we get it, and that's a good model. But our model is to share. So, quantum machines, best control hardware and software, make sure we understand that right. We're going to have product, Qolab Start, where we're going to sell you the complete system with our advanced software and advanced chips. We can make available to you our mount, which is designed for really good DC control with a superconducting ground plane. And that's a lot of things going on in that, and it's tested too. We have more advanced low-pass filters right now. Everyone's using Echosorb. I think maybe we invented that at UCSB. We think we have a more advanced product there that's going to work out better. We're still in test here. Noise, test for noise in the system, and we can chips and eventually hopefully get a foundry going. So that way you can do state-of-the-art experiments. Okay, next slide. So here's the mount. You have a picture on the right here of a 1 centimeter by 1 centimeter chips. with very short wire bonds between the chip and the mount. It's superconducting ground plane, so the DC control is good. There's good thermal control, good filtering, and the like, SMP connectors. If you want to look at it afterwards, it's right here. Next slide. At Qolab start, just a picture of our lab and the dilution refrigerator. This is the standard Blue Force refrigerator, wiring the same. And then we have a system that's cold that's been tested, for example, to have very low quasi-particle tunneling rates. So you don't have to worry about that kind of physics because it's done right. Next slide. And then here's our present day one qubit test chip with 6 qubits on here. And then here on the right is randomized benchmarking, where we're changing the frequency of the qubits. And right now, was it 99.935 for single qubit. So, that's okay. We're working on it. We're going to make it better. I want to get that down to 10 to the minus 4. We're still trying to tune everything up. Next slide. And then here, so again, quantum machines. We're really happy with the testing and bring up software. We're developing the systems. So to kind of an example of what we're doing here, for basic infrastructure, we think things like a cryoscope, and we have noise measurements to make sure your control is good. Basic qubit performance. You can do swap spectroscopy, that's T1 versus frequency, which you can learn about the TLS physics. Drag tuning, of course. Static and with Z pulses for your randomized benchmarking. And again, we want to also do simultaneous randomized benchmarking, and then we're getting to, we're having a 2-qubit chip we're testing too. So all these things we're going to be developing, obviously bigger and bigger chips over the time. And then the demo today, the items in blue are things that people can look at. Okay? So that's what I have before the demo. Are there any quick questions here?
Just curious that before you were in silicon quantum computing, so what's the advantage, disadvantage in that?
So the question was, I was in Australia for silicon quantum computing, and that was a very nice opportunity for me to learn about that. I would say the advantage with superconductivity right now is that we have very good system performance. We can do everything that you need to do, and that people are making obvious progress in it. And then for me, as we've come up with this, we think that there is a method with the semiconductor industry to really scale up rapidly. So, we'll see what happens with the different qubits, but we really like superconductors because they work. And I can kind of see the path and the direction to make these devices work way, way better than they're working now. But mostly, let's say, performance and also reliability, which is key. Any other questions? Are you guys ready for the demo? Okay, if there's no any other questions, I will turn it over to the demo. I don't know, how are we doing that? I'm not going to MC the demo.
Hey everyone, John's a tough act to follow, but we have a live demo running right now of a device that's on our fridge back in Madison at the Qolab headquarters. And so Tom over here is starting a series of qubit bring-up measurements, where I can't quite see what's happening. So right now, these are flux-tunable transmons, uncoupled at the moment, just something fairly simple. And we're just tuning up the qubit, first finding the upper sweet spot. There we are, tuning up.
Move the mic a little closer to you.
There we go.
Yeah.
Okay. We just saw tuning up the qubit in spectroscopy. Here's tuning up, Rabi on the qubit. And this sequence is all, at the moment, automated. This is running in the Quantum Machines QUAlibrate system here. And you can see this little roadmap on the left that shows a sequence of bring-up scripts. Here's bringing up qubit measurement. doing some optimization, getting the readout fidelities, looking at the I and the Q blobs, and optimizing things a little bit. And then here's, getting the frequency tuned up a little better with some Ramseys.
A little bit closer to us.
A little bit closer. Okay. There we go. Okay, and then now doing drag calibration. And for those of you that haven't used QUAlibrate before, you could do these all yourself. They can be queued up in a menu that's sort of behind the screen here. But right now it's set to run through these different measurements in an automated way. And this particular sequence builds up to doing randomized benchmarking here. And you can measure coherence. There's a T1 measurement. And then an echo.
And here we end this sequence. So in the star.
Okay. And that's the end of this particular sequence in that little roadmap that was up there. But I think we'll be available for questions. And so thanks for stopping by.